Okay, 9.3, we looked at basic trig proofs, and this builds on what we already started back in Objective 2, so I'm going to go ahead and put those notes up just so we can remind ourselves what we did. So in Objective 2, we looked at simplifying a trigonometric expression, and in this one, we're for the most part trying to reduce it down to one trigonometric function, so like number 10 reduced to cosine y. Today we aren't going to necessarily be getting it all the way down to one trigonometric expression, but we are going to be manipulating a trig expression like in 9.2 using many of the same concepts, the same ideas, both trigonometric and algebraic, in terms of using our identities, foiling, distributing, finding common denominators. So whatever mathematical manipulation would work to get one side of an equation to look like the other. Okay, and so I'd say probably one of the biggest differences between 9.2 and 9.3 is while in 9.2 we were trying to get our expressions down to one trigonometric function, we didn't really know what it was going to be up front, but we were pretty sure it was going to simplify down to one. 9.3, we know exactly what we're simplifying to, because with each of your problems, you're looking at an equation. And so because it's an equation, you have two sides to that equation, a left and a right. Now with this proof, it's going to be important that you don't switch sides of the equals. We are not solving for x. So in number 1 here, nothing on the left will ever come over to the right. And nothing on the right will move over to the left. We are going to be working with one side of the equation to get it to look like the other. Okay? Now, how you get it to look like the other, there's a wide variety of things you could do. So we wrote out, again, some of your trig identities. These are many of the same ones that were already in 9.2. New ones are right here, the complementary cofunctions. So reminder about those. And then we also have in the rules and strategies for trig proofs box some ideas for strategies you might use. Again, like 9.2, these aren't steps in that it's not like you do number 1 first and then number 2 and then number 3. They're strategies, they're tips. And so you'd be looking and going, okay, well, if I don't know exactly what to do, maybe I give number, I don't know, 3 a shot. If I notice that I have 2 fractions, maybe I try to combine them by finding a common denominator. If that doesn't work, well, maybe I look for, number 2. Can I factor? Do I have 2 squareds that are being subtracted? Because if so, then I could do difference of 2 squareds. Or do I have a trinomial factor that I could do, or something along those lines? I do want to highlight a couple of ones that we haven't talked about in a while. The first one, let me see if I can write it here, number 4, is if the denominator of a fraction consists of only one function, you could break up the fraction. In essence, what you're doing there is undoing common denominators. And so I'm going to show what that looks like in a short bit here. The other one I want to make sure we look at is number 7. And I actually referenced number 7 a little bit in 9.2 notes. If you watched those or were in class, I talked about the fact we're going to look at what it means to multiply by a conjugate again within the context of our 9.3 notes. And then if you'd like, you could use this idea, multiplying by the conjugate, in your 9.2 homework, because it's still an accurate algebraic step, just a different option. Okay? And so demonstrating those 2 ideas, I have 2 problems here. So the first one, the sine squared x over 1 plus cosine x. Sorry, I want that to be an x. I stole this from 9.2. This came off of number 10 there, although I did change them to x's instead of y's. So I stole it off of number 10. In number 10, in the 9.2 notes, it looks like we chose to, let's see. Oh, we chose to substitute sine squared y for 1 minus cosine squared y. And then because 1 minus cosine squared y were 2 squared values being subtracted, I could factor them as a difference of 2 squareds, 1 minus cosine y and 1 plus cosine y. Okay, which still works. I still, technically speaking, could do that on this sine squared x over 1 plus cosine x, but I want to demonstrate the conjugate idea. So a conjugate, we talked about this last semester, is when you have the same two terms, 1 and cosine x, but rather than having plus, you switch it to minus. Or if the original had been minus, you would have switched it to plus. So you have a different sign. What you're creating here are two things that, when multiplied, will create a difference of 2 squareds. That's what a conjugate does. Okay, but if we multiply it to the bottom, we also have to do it to the top. Okay, and so this would simplify to sine squared x times 1 minus cosine x on top. On bottom here, foiling these out, 1 times 1 is 1. The negative cosine x and positive cosine x for the outside and inside will cancel. And then we have minus cosine squared x for the last. And 1 minus cosine squared x is related to our Pythagorean theorem, or sorry, Pythagorean identity. 1 is the same thing as sine squared plus cosine squared. The cosines then cancel. Leave me with sine squared x times 1 minus cosine x over sine squared x, and the sine squared x's will cancel, leaving me with just 1 minus cosine x. Okay? So that's what it means to multiply by the conjugate. Within your proofs, the reason you might choose to multiply by a conjugate is if you're looking at the two sides of the equation, or potentially somewhere else inside of your equation, you notice like, wow, I have these two ideas. Maybe I'm looking at a, I don't know, cosecant x plus 1 on one side of the equals, and maybe there's some other stuff with it, and a cosecant x minus 1 on the other side of the equation. Again, there might be some stuff with that, but if you're looking at like, well, wait, why did the plus become a minus? There's a good chance it probably happened through some type of multiplying by the conjugate. Not all the time, but a lot of the times. And so maybe that would be then a strategy you might try. Could I multiply with a conjugate, see if that helps me manipulate it? Okay, the second one here is to demonstrate step 4 that I starred here. If the denominator of a fraction consists of only one function, break up the fraction. And that one function in the denominator could be anything. Okay, but say you were looking at something like this, and a secant x plus cosecant x over secant squared x. Because these two things in the numerator have the same denominator, I could rewrite them as two different fractions as long as I leave them both with that original denominator. Okay, like I said earlier, what we're doing here in splitting up our fraction is essentially undoing the common denominator idea, right? If I went the reverse direction, went from this side to that side, I'd be saying, oh, this right side has the same denominator, therefore I can add my numerator and combine them as one fraction. We're just undoing that step. Okay, what this would allow you to potentially do is maybe simplify the secant x's in that first term. And then maybe you rewrite with reciprocals if that was necessary. 1 over secant is the same thing as cosecant. Cosine. And then 1 over secant squared would be cosine squared. Cosecant is the same thing as 1 over sine. And so maybe you take some route like that. This step you would use if you were ever looking at something, you're like, well, wait, I have one fraction, but my other side of my equation has two different terms in it. How does that happen? Chances are probably through splitting the fraction at some point. If you find yourself going from one fraction to 2 on the other side of the equals. Okay. Okay, so demonstrating this proof idea now within context. Similar to 9.2, it's going to be challenging to, potentially speaking, practice these on your own, only in that there's more than one way to solve these problems. You're getting one side of the equals to look like the other, and so the first differing way is to work with a different side of the equation. In number 1, I could work with the left side and get it to look like the right, or I could look at the right side and get it to look like the left. For me, I tend to always start with the one that looks the most complicated, and I try to simplify it to look like the one that looks a little simpler. Sometimes though, you're looking at the two sides of the equation going, they kind of look like they're the same level of difficulty. Well, then you pick one and you manipulate it. And if it seems like that route's maybe getting more challenging than the other, then go back to the beginning, switch sides, and see if the other way is a little bit easier for you. But because there are so many different ways through these problems, it's going to be imperative that if you try one of these on your own and then watch the video and I take it a different route than you do, it doesn't necessarily mean that yours is wrong. Take a picture, send it to me. I can check your work for you, help you figure out where you got off a little bit. I can even model it on a different video for you if you'd like, working through it your route. But it's pretty imperative that you advocate for the way that your brain is kind of processing the problem. And if your way doesn't work, I'll tell you, and I'll help you kind of figure out a way that does work. But there's not one way, and so you can't restrict yourself to thinking that the way I demonstrate on the video is the right way. When I did these in class, I had people talk to their partner, I drew sticks, we talked about different ways of doing it, and people solved these problems different ways. You're learning this at home, you obviously don't have the ability to talk to your classmates, so talk to me. Take a picture, send it to me. This is what I'm thinking. Would this work? That kind of thing. Okay. Okay, so for each of these, my recommendation is to pause the video, work through it on your own, see if you can get one side to match the other. Remember, nothing will switch sides of the equals. Whatever starts on the left needs to stay on the left. Whatever starts on the right needs to stay on the right. Restart the video then when you either have an answer or are stuck and want to kind of hear my explanation or hear up to the point you're stuck at, and then pause the video again, something like that. But go ahead and pause the video, give number one a shot, and restart it when you're ready. Okay, so in number one, for me, I look at the left side of the equation, and that one looks the most complicated to me. So for me, I'd probably work on that left side, try to get it to look like the right. And so I'm sitting there going, okay, well, how do I get cosine squared out of this? Well, I know sine squared. I could use this Pythagorean identity potentially to get a cosine squared out of sine squared. I also know that tangent could be rewritten as sine over cosine. And so tangent squared could be sine squared over cosine squared, and that could be how I get my cosine squared. If you aren't sure, you pick one of them. For me, I'm looking at this going, well, I know that tangent has a sine squared then in it as well. And so maybe if I use the tangent identity, I might be able to simplify the sine squareds. I don't know. Let's give it a shot. Okay, so changing tangent into sine over cosine. Okay, now I need to get it to be just equal to cosine squared, that right side of my equation. Okay, well, I know that dividing by a fraction is the same thing as multiplying by its reciprocal. So maybe I change this to times cosine squared over sine squared. Oh, and then I'm looking and I'm noticing that the sine squareds then are going to simplify. So I'm left with cosine squared equals cosine squared. My proof is done, QED. Okay, go ahead and pause the video, give number two a shot, restart it when you are ready. Okay, so number two, when we did this one in class, some people worked with the left side of the equation, others worked with the right. They obviously have two very different routes through the problem. On my end, I myself chose to work through the right when I was making my answer key. The right side of the equation looks a little bit more complicated to me. And so I looked at the right side. I said, okay, I'm going to go ahead and leave the left side alone. Just remember, nothing switches sides. Again, that right side going, okay, how can I get this to have a cosine squared minus sine squared? Well, I noticed I already have kind of a minus sine squared idea there. So the first thing I'm going to focus on is how could I get it to be a cosine squared? Well, I notice I have 1. And 1 I know has actually a couple of potential identities. But the one I'm going to focus on is this guy here, because that one then would have a cosine squared in it. And so I'm going to go ahead and take sine squared plus cosine squared, and I'm going to substitute it into my 1 spot. So sine squared plus cosine squared into 1. I'm hoping that this will allow me to finish simplifying. I then notice that I can combine like terms. The left side alone. On the right, we have a sine squared beta minus 2 sine squared beta, which can simplify to just minus sine squared beta. And I've got my two sides equal, so my proof is done, QED. Okay, so those two I would call kind of our more straightforward ones, a little bit more basic. We're going to get more complex as we continue here. So in number 3, I'm going to pause again, give you a chance to pause the video, try it on your own, restart it when you're ready. But these are the ones where we're probably going to start to see a lot more variety in steps, and you might get stuck. So again, send me a picture. I'll help you figure out where you got off, and we'll get that fixed. Okay. Okay, number 3. Number 3. In class, people, almost everyone worked with the left side of the equation. I don't think I saw anyone work with the right. I myself worked with the left as well. With the left side of the equation, as people were working with it, I saw some who multiplied these terms together, so kind of simplified the secant to the 6th alpha, secant alpha, tangent alpha in the first term, and then the secant to the 4th alpha, secant alpha, tangent alpha in the second term. I saw some people who did that. Some others chose to factor, and then I saw actually 2 different choices when it came to that factoring. Some factored out just a secant alpha, tangent alpha. Some factored out both the secant alpha, tangent alpha, and the secant to the 4th alpha that these 2 terms have in common. All of these routes work. For me, when I did it, I did choose to kind of multiply these terms together initially. So secant to the 7th alpha, tangent alpha, minus secant to the 5th alpha, tangent alpha. Okay. And then I looked at this and went, okay, well, what else could happen? Well, I noticed that my 2 terms have a GCF. They both have a secant to the 5th alpha in common and a tangent alpha in common. So if I could factor those out. So if I pulled a secant to the 5th alpha, tangent alpha out of my first term, I'd be left with a secant squared alpha. And if I pulled a secant to the 5th alpha, tangent alpha out of my second term, I'd be left with minus 1. Okay, so now you're looking at your 2 sides of the equation going, man, it's getting a lot closer here. We have a secant to the 5th alpha in common, so something needs to happen with that secant squared alpha minus 1 to get it to be, to get it to go away, to get it turned into a tangent somehow. And so then I go back and I look at my trigonometric identities here, and I notice that right here, my secant squared is the same thing as tangent squared plus 1. Right, so I could come down to number 3, and in my secant squared, I could substitute in tangent squared plus 1. Okay. Well, the nice thing about that then is that the 1s are going to simplify. They're going to cancel each other out, actually, technically speaking. So we'd have just the tangent squared alpha left inside of my quantity, which will allow the 2 tangents on the left side of my equation to combine to become tangent cubed alpha. And now that my 2 sides of my equation are equivalent, my proof is done, QED. Okay. Okay, number 4, go ahead and pause the video, give number 4 a shot, restart it when you're ready. Okay, number 4, in class, I saw people take, for the most part, it looked like 2 different routes through this. So some people worked on the left, some people worked on the right. For those who worked on the left, which is actually the way I'm going to walk through it, most looked at splitting the fraction. For those who worked on the right, most looked at finding common denominators and kind of went that route. As I said earlier, the way I'm going to work through it is on the left. That's the route my brain kind of went when I first looked at this problem. I looked at the left, said that one looks more complicated. I'm going to try to get that one to look like the right. And so when you're looking at tangent x plus cotangent y over tangent x cotangent y, the first thing I notice is that between the left side of the equation and the right side of the equation, there are no sines or cosines that all of a sudden come into being. It's very tempting with tangents and cotangents to want to switch right into sines and cosines. And while that's not necessarily wrong, it does a lot of times in a problem like this cause more work than you need to solve the problem. Because if you switch into sines and cosines on the left, you're going to have to switch back again at some point to get it to match the right. And so the first thing I did is say, well, I'm not going to switch into sines and cosines. The other thing that I noticed as I looked at the two sides of my equation is that on the left, I have one entire fraction, where on the right, I have two individual pieces. And that, for me, cued this manipulation strategy that we looked at earlier, which is splitting the fraction. Like I said, when we walked through that manipulation step, I tend to use that step when I notice I have one thing on one side and two on the other, or something like that. And so I went ahead and said, okay, let me go ahead and split that fraction then, tangent x plus cotangent y, and again, make sure that both terms keep that same denominator. They have to have the same denominator in order to have been combined in the first place. Okay, and so then taking a look at this, each term now can simplify. The tangent x's can simplify in the first term, and the cotangent y's in the second term. And then looking at your two sides of the equation, these look very, very similar. I still have a 1 over cotangent though, instead of just like a tangent or a cotangent. And so that's when your identities are going to come into play up here. That 1 over cotangent is the same thing as tangent, and 1 over tangent is the same thing as cotangent. Okay. So then coming back down here, 1 over cotangent is the same thing as tangent, and 1 over tangent is the same thing as cotangent. And you've got your two sides to be equal to each other. And so your proof is done, QED. Excuse me. Okay, number 5, go ahead and pause the video, give number 5 a shot, restart it when you're ready. When we did this in class, most people chose to work on the left, which is that's the way I'm going to do it. They chose to multiply by the conjugate. For those who chose to work with the right side of the equation, the secant plus tangent, they usually went the route of finding a common denominator and then multiplying by the conjugate, is what I saw for most people. And again, there were a couple of other routes, but those were, I'd say, the two most common. Okay. The other thing we talked about in class is if you ever have a variable that you don't really want to have to keep writing over and over again, you can always change that variable if you'd like. Just notate that you're going to do so and then make sure you're consistent. Okay. So again, most people that I saw in class worked with the left side of the equation and chose to multiply by the conjugate. I myself actually did the right side of the equation when I made my answer key, but I'll go ahead and go with the left because that was the majority where it seemed like student comfortability. Multiplying by the conjugate is a good idea to have. Multiplying by the conjugate again, when you notice you have a minus on one side and a plus on the other or something like that, especially if they happen to be the same terms. Now these don't happen to be the same, but if this one had also been a 1 plus sign, then that would have been a really good indication to try a conjugate. But that's what a conjugate does, is it introduces the reverse sign, the opposite sign. Okay, so multiplying by our conjugate here, my numerator then becomes cosine x times 1 plus sine x. Over in my denominator, I have 1 minus sine squared x when I FOIL that out. Okay. And so then you're looking at, okay, well, what else needs to happen? Well, I know 1 minus sine squared is linked to this trigonometric identity up here. Sine squared x plus cosine squared x equals 1. And so I'm going to take that sine squared plus cosine squared and substitute it into 1. Okay. This then allows for a couple of different simplification steps to take place. First up, my sine squareds are going to cancel. And then I have a cosine on top and 2 cosines on bottom, and so one of those cosines can cancel. So I'm looking at 1 plus sine x over cosine x equals secant x plus tangent x. Okay, so then you're looking at the two sides of your equation going, okay, well, I've got this also starting to look very much like number 4. I've got one fraction on the left and 2 different terms on the right. So maybe I try splitting the fraction. Just make sure that when you do so, that both terms still keep their denominator. Okay. And then simplifying, we're almost there. 1 over cosine is the same thing as secant. And sine x cosine x is this over cosine x is the same thing as tangent x. And with that step, our proof is done. QED. Okay, 2 more proofs here. Go ahead and take a look at number 6. Pause the video. Restart it again when you are ready. Okay, in number 6, this one, depending on which side of the equation you work on, you actually end up taking the first or the same first step. Just how that first step looks, that's going to be different. So I'm going to work on the right side of the equation for this one. Okay. Both sides of the equation, whichever one you choose to work with, are going to require a multiplying by the conjugate. Well, I don't know if require is exactly right. There might be another way through, but I'd say in class, I saw most people multiplying by the conjugate. If you're working with the left side of the equation, then you'd be multiplying by 1 plus cosine theta. Well, working with the right side, we'd be working with 1 minus cosine theta. Again, like number 5, the reason we are thinking about multiplying by the conjugate is because we see the minus on one side and the plus on the other. And in this one, we, additionally speaking, supporting that idea, see a 1 and a cosine that are exactly the same on either side of the equation. So your 2 terms here are equivalent. That's a good indication that when you have the same terms but opposite signs, it's probably multiplying by the conjugate. Okay? So leaving my left side alone here. On the right side, my numerator then becomes 1 minus cosine squared when I FOIL that out. My denominator is sine theta times 1 minus cosine theta. Using our Pythagorean identity up here, the sine squared plus cosine squared equals 1. I can substitute sine squared plus cosine squared into my 1 spot. Again, leaving the left alone. Substitute sine squared plus cosine squared into my 1 spot. Okay. This will allow the cosine squareds in the numerator on the right side of my equation to simplify, leaving me with just sine squared. And then now that I've simplified that step, my numerator has 2 signs on the right side. My denominator has 1 sign, so one of the signs can simplify. leaving me with sine theta over 1 minus cosine theta on both sides of my equals. So my proof is done. QED. Okay, last but not least, number 7. Go ahead and pause the video, give number 7 a shot, and restart it when you are ready. Okay, when we did this one in class, I'm pretty sure every single person worked with the left side of the equation, which is the one that I worked with myself when I was making my answer key. If you tried to work with the right side, I'm not saying that that wouldn't work. I'd have to work it out. I'd have to look at your work myself. So if you are wanting to check the right side, like I said, take a picture, send it to me. I'm more than happy to take a look at it and to see if we can find a way through the problem. But like I said, most people worked with the left side of the equation. I will say that working with the left side probably is going to be faster for this one, because the numerator on that left side is a cubic factor. So cubic factoring reminder, if we have an a cubed plus b cubed, and we know we can defactor that, it's a and then same b, a squared, opposite ab, always positive, b squared. And if it was a cubed minus b cubed, it would be a same b, a squared, opposite ab, always positive b squared. So cubic factoring, which also is from last semester. Okay, so using that idea, on number 7, we notice that our a would be the tangent x, so a cubed. B would be 1. 1 cubed is 1. And so if I factor that, a same b, a squared, opposite ab, always positive, b squared, which will allow on the left side of my equation there for the tangent x minus 1 to end up canceling, leaving me with tangent squared x plus tangent x plus 1 on both sides of the equation. And your proof is done. And that's 9.3.